And with that, let me introduce our first speaker of this afternoon, and that's Professor Maria Graan. She's an associate professor in energy systems analysis and also the director of a collaboration platform, Energy Area of Advance at the Chalmers University of Technology, where she's working in the Department of Mechanics and Maritime Sciences. She aims to provide long-term and global perspectives on the transition into a fossil-free energy system, focusing on transport solutions and the role of different fuel options, looking specifically, for instance, into hydrogen, into electrofuels, what challenges are there, what possibilities are there, and looking both at cost competitiveness and environmental effects. So with that, Maria, I hand it over to you. Looking forward to your presentation.
Thank you very much. This is a presentation about the e-fuels, so the big picture, focusing on the role of electro-methanol. So I put the slides together to show 10 insights from our research that we have been conducting in the last 5 years on under what circumstances electrofuels could become an interesting option in the fuel mix of the transport sector. So just starting with having an idea of what we mean with electrofuels, so that the production of electrofuels, we see that they're starting with electricity and we need hydrogen, and the hydrogen is combined with the carbon that either can be coming from the biofuel or they can come from any types of combustion where they have any carbon dioxide in the exhaust, or they can come from direct air capture or from the seawater. And then you need a synthesis reactor, and for example you have the Sabatier reactor or the Fischer-Tropsch reactor on the market, methanol reactors as well. So then we can produce electrofuels that is on the same molecules as the biofuels. So we can blend electrofuels with the biofuels. So I would like to start on this big picture under what circumstances could the electrofuels become cost competitive. So I have first, a review of the electrofuel production cost that I would like to share some slides from. And this is a messy picture maybe, I will try to walk you through. So we're trying first to compare the electrohydrogen with electromethane, electromethanol, electro-DME, electro-Fischer-Tropsch diesel, and then electrogasoline through the methanol to gasoline process. And you can see that there are different lengths of the bars here. So we have in our comparisons try to find a base case, but then we also, since it's a very broad range of data available in the literature, so we combined all the best data and all the worst data, so we also have a shorter bar and a longer bar. So what can we learn from this? We can learn that since there are so many different approaches among authors, so then we see that when data is harmonized, we compare the middle one with the middle ones and the short the best one with the best ones. Then we see that there are not that much difference between the different fuel options, which makes perfectly sense because the cost is dominated by the electrolyzer and also the cost of electricity. So that the end part, when you have the fuel synthesis and the CO2 capture part, is only a small part. But you can also see that that uncertainties that is here in the striped part of it, it's relatively large as well. And this uncertainty cost is typically not taken into account in some of the academic literature that we have found, but it's almost always there when you find literature from consultancy or those that are building the facilities. So this uncertainty factor could be a factor of 1 up to a factor of 5 of the investment cost. But the 3 different costs for the electrolyzers, the investment cost and operation and maintenance cost, and then also the stack replacement cost is one of the dominating costs. And just for the insight 3, we can also see that those costs that are dominating for the electrolyzer and also for the electricity, we have a trend that it is going downwards, that there is a great potential to reduce the cost in future for electrolyzers and for the electricity, which are the dominating parts. Then we, in the same study, also made analysis of trying to understand the role of capacity factor. How many hours per year do you run your facility at full capacity? So if you want to just have your facility running on what we can call free or excess electricity, maybe 10% of the year, you see that per megawatt hour of electro-methanol, it will be still a high cost per megawatt hour of the methanol, up to about 400. Whereas the more you can utilize the facility over the year, the higher the cost part, which is the electricity cost, increases per megawatt hour of produced fuels. But an insight is that it is relevant to have your facility running at least 40% of the total amount of hour per year to get the lower part of the production cost, and then it's phased out. So around, in this analysis here, around 100 euro per megawatt hour could be a future production cost. And then we compared the production cost with more advanced biofuels. So insight 6 is that we can see that they are in the same size of order as the more advanced biofuels. So then I would like to share you also some slides and some results from a recent study that we have done on the big picture, and that is, under what circumstances could electrofuels become cost competitive in the shipping sector? So here we are first comparing the different production costs, including also hydrogen and battery. And then we also include the total cost of ownership, so that we include in the investments also in the propulsion technologies. So what we're looking at are the combination of the different electricity sources, biomass sources, and the fossil sources for the different types of fuels, including methanol, but there are also DME and HVO and liquefied methane gas from gasification, liquefied biogas from anaerobic digestion of household waste. We have ammonia, we have the liquefied hydrogen, and we have electricity. And we combine them in 4-stroke engines, 2-stroke engines, battery electric, and also fuel cell electric propulsions. And then we combine them also for large ferries, for general cargo ships, bulk carrier, and container ships. And in the end here, it's not shown here, we also compare them for different distances. If you run the ferry on a long or medium or maybe a short distance. So here are all the different combinations that we have gone from the left-hand side of the picture, from the different type of bioenergy and electricity sources. And on the right-hand side, you see that we have grouped the different fuel into the green part, which are the biofuels. So we have biomethanol, and in the blue part, we have the kind of hybrid. So it's an electric biomethanol where we utilize the excess CO2 from the gasification and meet up with more hydrogen, so that we have, in the blue case, a hybrid fuel, electro biofuel. And in the more orange field here, we have the electrofuels, where we then have e-methanol as one of the options. And then we compare them also with the more yellow, in the end here, liquefied hydrogen, and also electricity in the battery electric propulsions. So from the same study, then here is our base case of the fuel production cost. So I have circled the one that is on methanol. So if we go for the biomethanol, we need the production cost, but also it's an infrastructure cost, the gray one on the top. And compare that then with the electro biomethanol, the hybrid version, which are the more blue-green, which you can see that the base case cost adds up to 69 euro per megawatt hour. And then we have 91 euro per megawatt hour for the hybrid version, whereas the electric methanol is on the size of 119 euro per megawatt hour. And for the liquefied hydrogen, we have a little bit higher cost. Because you can also see that the infrastructure adds up part of the total cost for the fuel production. And this is also a bit of a messy picture. I will walk you through this one as well. So this is an example of the results of also the base case, and then this is for large ferries. And in the matrix, you can see there are 3 columns: short distance, medium distance, and long distance. And within the short and medium and long distance, we have the comparison of internal combustion engines, fuel cells, and battery electric vehicles as the 3 different options within each of the range. And then on the different rows, you can see that there are the same blocks of the biofuels on top, the bioelectrofuels in the middle, and then we have the electrofuels on the lower part of the block. And below the blocks, we have liquefied hydrogen and electricity in battery electric propulsion as well. So within the block, you have a color coding within each block and also within each range. So the darker the green, the cheaper the option. And the opposite, the redder and the darker the red is, that is the more expensive options. So I've circled again the biomethanol option. So for the short distance, in the ICE option, it's 2.0 million euros for the total cost of ownership. Then we have added, as I said, a cost for the fuel production is there and the fuel infrastructure is there. But we also have an annuitized investment in the propulsion technologies. We have a cost for energy storage, and we also have included reduced income due to less cargo space. So the total cost of ownership, we can see that within each block, it is the methanol case that is the lowest total cost of ownership. Whereas we see for the fuel cells that they are becoming the higher option. And then we assume that we can run the fuel cells on both liquefied methane and also on methanol, apart from the hydrogen option, which is in the bottom then. So insight 7 that I would like to share with you is that the methanol and the e-methanol may be the lowest cost options from the TCO perspective in the shipping sector. But it's of course complex. So when we're trying to elaborate with the different possibilities of combining the options, I would like to share you one result that sometimes we have the more expensive methanol, which are the 2 first columns or the bars here, represented by electro-methanol, for example. Then, so if we have a fuel that is in this case 180 euro per megawatt hour, then we can see that the total cost of ownerships is lower if you have run it in the fuel cell compared to the internal combustion engines, if you compare the 2 first bars. On the opposite then, for the 2 last bars, if you have a cheap methanol, if you produce it from biomass, for example, then it will be the opposite, that the total cost of ownership will be lower if you run it in an internal combustion engine compared to the fuel cells, although they are not that different. But it is an interesting finding, I think. So that's the insight 8. So very quickly, I would like also to show you 2 slides from an ongoing project that we have on Chalmers right now. So we have a hydrogen methanol case. It's an EU project called HyMeth ship. So in this ship, we fuel the ship with electro-methanol. Then we have a reformer on board producing hydrogen. So hydrogen is used to propel the vessel. And then it is a possibility when you convert it into hydrogen to store the CO2, to capture and store the CO2. And also the heat from the internal combustion engine can be used in the reforming process. So that makes more sense to have an internal combustion engine on hydrogen compared to fuel cells on hydrogen, since you need the hydrogen heat, the heat for the reforming. But it is the point is that you can have the CO2 stored in the tank on board, and then we'll get to the shore and you can unload the CO2 and produce new electro-methanol. So it will be a closed loop of the CO2 in this case. So just sharing the results on cost comparison for the HIMETH ship, which is the last column here. So you see that there are small parts between the black and the orange. That is the additional equipment needed for the reforming and for the HIMETH ship concept. So just comparing the two last bars when you have electro-methanol in this. Is my time running out? I see you coming back now, Sebastian.
Go ahead.
Go ahead. I have like 2 more minutes, if it's all right. It's just comparing the two bars here that we can see that if you have electro-methanol, not in the HIMETH ship concept, but running the vessel also on the methanol itself, it becomes more expensive compared to the HIMETH ship. This is because that we assume that the electro-methanol is produced from direct air capture of the CO2, whereas we have a closed cycle of the CO2 in the HIMETH ship. And the two first bars, they are the fossil options, where they have a methanol in internal combustion engines, natural gas-based methanol, but you also have the MGO in internal combustion engines. So although if you put on a carbon tax of about 100 euro per ton of the carbon tax, they are still the lower cost options with the fossil fuels. So it's, of course, a challenge to get the cost competitiveness for these new interesting options. I think maybe I should end here. So my insight 10 was trying to understand the long-term cost competitiveness in the energy systems model, where we can see that electrofuels and also synfuels, which here are also carbon dioxide-based fuels, but the hydrogen comes from the thermal split of water instead of electrolysis of water. But the yellow and the purple parts here can make sense in the cost competitiveness, cost minimizing model. At least when we assume that it will be difficult to store CO2 underground. So thank you so much for listening.
Thanks, Maria. Very interesting points you touch on. We do have a couple of questions lined up for you, I think. I'm just waiting for the first one to appear. The first one is when you consider biofuels and your matrix of different options, whether you consider land use and water consumption in that assessment.
Yes, absolutely. So we have the water consumption. That is very small part of the. It's so small that it's not even shown. So the cost for water needed to produce the electrofuels are also included in here.
Okay, thank you. And then another question for clarification, whether the TCO calculation indeed included the costs for carbon capture.
Yes, it should also be carbon capture included when you have the electrofuels.
Yeah.
And in the top of my head now, I don't remember what type of carbon capture that we assumed. Many times when we have the base case, we assume that we have carbon capture from exhaust streams from the factories.
Yeah.
So then it's around between 30 and 50 euros per ton. I think that was also the case in this base case here, but I'm a bit unsure.
Okay,
I have added the references as you can.
Great, thank you.
Read it more.
Yeah, then equally important, I think, in the assessment is the efficiency estimates you took for the fuel cell solution and the combustion engine solution operating on methanol, for instance. Can you remember what type of efficiencies you started from there?
The efficiencies are for the combustion part or for the propulsion part. They are relatively optimistic. So if I have I may be mistaken now, but I think it's 45% between 45 and 50% for the internal combustion engines, and slightly higher for the fuel cells, but not much higher.
Yeah. Okay, thanks for that. Then also one that's popping up quite frequently these days, we see various figures out there on the production cost of ammonia versus methanol. And here one of your slides showed that ammonia ends up being more expensive, whereas there's definitely also numbers around where the opposite is shown. Do you have any insights as to what causes the difference and what's probably the right answer?
Yeah, ammonia, we were surprised that ammonia was so close to the other more common options as methanol, for example. It could be, from a cost perspective, a good case for ammonia. And as we also mentioned before lunch, we don't see them as competitors. We see them as complementing towards getting fossil-free transport sector. So we welcome, of course, all the other challenges that it's not cost-related to be improved. But I don't remember now why exactly they are slightly higher for ammonia compared to methanol.
Okay, then we might come back to that during the Q&A session. Thank you very much, Maria.